Hello everyone, we are at the topic of diodes. Today we are going to look at the structure of the PN junction diode and the IV characteristics of the diodes. The IV characteristic graph of a PN junction diode is provided in this figure in here. If we label the voltage across the diode as VD, plus, minus, and VD, and the current that flows through the diode as ID, and then when VD has a negative value or VD is less than 0, we're going to say that the diode is reverse biased, and when VD is positive, we're going to say that the diode is forward biased. Now the diode does not turn on immediately when VD is slightly above 0 volts. Rather, it turns on, for example, for the case of a silicon diode, it turns on at around 0.6 volts to 0.7 volts. This voltage is the cut-in voltage or the built-in potential of a silicon junction diode. The diode IV equation is a nonlinear equation, as you can see in this equation. ID is exponentially related to VD, or the voltage across the diode. In this equation, IS is the saturation current, which is a quantity in the range of 10 to the negative 9 to 10 to the negative 18 amps. And VT is called the thermal voltage. Its value at room temperature is about 26 millivolts. The definitions of these quantities and the derivation of this current voltage equation for ID is beyond the scope of this course. You're going to see these derivations and calculate them in future courses. In EC65, we are not going to use a nonlinear IV equation for the diode. Instead, we are going to use a linear model for these equations. So, the diode piecewise linear model consists of two lines, one for the case that the diode is off and one for the case that the diode is on. In the piecewise linear model, we're going to assume that ID is equal to 0 when the diode is off, which is the equation for this line. ID is equal to 0, and when the diode is on, VD is equal to VD naught, which is the equation for the second line. Now I can write VD as V1 minus V2, which is the node voltage. V1 and V2 are the node voltages at two terminals of the diode. So assuming that we have a silicon diode with VD naught equal to 0.7 volts, if V1 minus V2 is less than 0, then the diode is reverse biased and ID is equal to 0. When VD is a positive value but less than 0.7 volts, the diode is forward biased, but it's not on yet. As a result, ID is equal to 0. When V1 minus V2 or VD is equal to VD naught, the diode is forward biased and on. As a result, ID is going to be greater than or equal to 0, and the voltage across the diode is going to be a constant value equals to 0.7 volts. These are the equations for the piecewise linear model. Diode on, VD is VD naught, ID is greater than or equal to 0. Diode off means ID equals to 0 and VD is less than VD naught. For the case of silicon, the cut-in voltage or the built-in potential is about 0.6 to 0.7 volts. The circuit models that we're going to use for the diodes are, when the diode is off, we're going to represent it with an open circuit, as you can see in here, and when the diode is on, we're going to represent it with a constant voltage drop model. That is the symbol of a voltage source with its voltage value equal to VD naught. But this doesn't mean that the diode supplies voltage. It just means that when the diode is on, a voltage equal to VD naught is going to be dropped across the diode, and this voltage is a constant. Let's see how we can solve the diode circuits using the models that we derived and the piecewise linear equations that we calculated for two states of the diodes. One way to solve the diode circuit is to assume a state of a diode, either on or off, and then find the current or voltage across the diode and compare it with the equation related to that state. For example, in the given circuit, when the diode is off, ID is going to be equal to 0 and the voltage across the diode, or VD, is going to be less than, it's supposed to be less than VD naught. Now, we can replace the diode with its circuit model for the office state, which is an open circuit, and here calculate VD, or the voltage across the diode, and compare it with VD naught. If it is less than VD naught, then the diode, our assumption was correct and the diode is off. Or we can assume that the diode is on, and we know that the current and voltage equation of the diode in the linear model, for the case that the diode is on, our ID is greater than or equal to 0 and VD equals to VD naught. Now in the circuit, we're going to replace the diode with its circuit model for the case of the diode being on, which is going to be the symbol of the voltage source, or the constant voltage drop model, and the voltage of this constant voltage drop model is equal to VD naught. Now we're going to calculate ID in this circuit and compare it with 0. If it is greater than 0, our assumption was correct. Okay, let's solve an example. Now this is the same circuit that we just saw, but here I have some values for VI, R, and I know the cut-in voltage or built-in potential of the silicon diode, which is given as 0.7 volts. So I'm going to start by assuming a state for the diode. Let's say that we're going to assume that the diode is off. This assumption means that ID is equal to 0 and VD is less than VD naught. If I redraw the circuit using the circuit model for the diode when it is off, I'm going to have something like this. So when the diode is off, I can replace it with an open circuit. The voltage is equal to VD and ID is going to be equal to 0, and R is 1 kilo ohm, VI is equal to 5 volts. I can write KVL in this circuit, so I'm going to say VI is equal to 1K multiplied by ID plus VD. Because ID is equal to 0, VI is going to be equal to VD, which is equal to 5 volts. Now I need to compare this VD with the assumption that I have in here. Because I started by assuming that the diode is off, I knew that for the diode being off, VD must be smaller than VD naught. However, this is greater than 0.7 volts. As a result, our assumption was incorrect. So the diode is not off with this condition. In the second step, I'm going to assume that the diode is on, and the diode is on. With this assumption, I expect ID to be greater than or equal to 0 and VD to be equal to VD naught. The circuit model, I'm going to draw the circuit again, and that is going to be this 1K, and I'm going to replace the diode with its constant voltage drop model of 0.7 volts, and this is again my ID, and this is VI, which is 5 volts. Now again I can write KVL in here. VI equals to 1 kilo ohm multiplied by ID plus 0.7 volts. Now VD is equal to 0.7 volts, so I'm going to plug in VD as 0.7 volts here. The inequality that I need to check is this one in here. ID must be greater than or equal to 0. Let's calculate ID. It's equal to 5 volts minus 0.7 volts divided by 1 kilo ohm, which is going to be 4.3 milliamps. This is greater than 0. As a result, our assumption was correct and the diode is on. The second example is the same problem, but in this problem we would like to find the range of VI for which the diode will be on and the range of VI for which the diode is going to be off. So again, when the diode is on, I know that ID is going to be greater than or equal to 0 and VD is going to be equal to VD naught. From there, I can write one KVL in this equation and write VI equals to R times ID plus VD. When the diode is on, I'm going to replace VD with VD naught. So I'm going to say VI equals to R times ID plus 0.7 volts. I would like to solve for IDs to be able to use this inequality and find the range of VI for which the diode is on. So from there, ID is equal to VI minus 0.7 volts divided by R. And now I want this ID to be greater than or equal to 0, again using this inequality. So it's going to be greater than or equal to 0. From there, VI must be greater than or equal to 0.7 volts. So for VI values greater than 0.7 volts, the diode is going to turn on. 0.7 volts of the voltage that is supplied by this voltage source is going to drop across the diode, and the rest is going to drop across the resistor R. So if VI increases from 0.7 volts, the voltage drop across the resistor is going to increase. Also, the current through in this circuit is going to increase, but the voltage across the diode is going to stay at a constant value of VD0. For this range, for VI greater than or equal to 0.7 volt, diode is on. VD is going to be equal to VD0, and ID is going to be greater than or equal to 0. Let's solve it for the second case, that is when the diode is off. So when the diode is off, then ID is going to be equal to 0 and VD is less than VD0. Again, I'm going to write the same KVL. VI is equal to R times ID plus VD, and ID is equal to 0. From there, VI is equal to VD. Because I want VD to be less than VD0, in other words, voltage across the diode is less than VD0 when the diode is off. From there, I know that VI must be less than VD0 for the diode to be off. So I have for VI less than VD0, the diode is off, and ID is going to be equal to 0. So ID is equal to 0 and VD is less than VD0. In summary, today we looked at the diode IV characteristic graph, and we looked at the forward bias and reverse bias conditions of the PN junction diodes, and also we looked at the piecewise linear model of the diode, and we solved a couple of diode circuit problems. Thank you for watching.